Okay, let's dive right into this. Welcome to this explainer. Today, we're exploring a truly fascinating paradox in modern technology. We're going to look at exactly why your premium, incredibly expensive smartphone still overheats, despite being packed with absolute space-age cooling materials like graphene and multi-layer vapor chambers. It's this brilliant mystery of physics and engineering, and as you'll see, the answers are all right here in the data. Think about your own experience for a second. Whether you're rendering a 4K video, playing an intense high frame rate game, or spinning up one of those new on-device AI tools, we really need to ask this fundamental question. Why do multi-thousand-dollar devices still double as expensive hand warmers? I mean, you'd think we would have solved this by now, right? Well, it turns out the physics of the situation are a lot more stubborn than we might like to admit. Here's our structural roadmap for the explainer. We're covering the thermal management paradox, the evolution of mobile cooling, inside modern cooling tech, the hidden physics bottlenecks, how different brands adapt, and wrapping up with the future of cooling. Kicking things off with Section 1, the thermal management paradox. Let's look at how the massive power density of modern chips is constantly outpacing the physical capabilities of your phone's chassis. So when your games suddenly start lagging or your screen unexpectedly dims, what you're actually experiencing is thermal throttling. The device literally has to intentionally slow its own brain down to lower heat generation. If it didn't do this, the internal components would suffer permanent physical damage. It's basically your phone's unavoidable self-defense mechanism kicking in. Moving right along to Section 2, evolution of mobile cooling. Let's see how the engineering has frantically tried to keep pace with these chips over the years. Just look at how rapidly this had to evolve. Pre-2015, we were stuck in the conduction-limited era, mostly relying on basic silicone greases, which honestly led to terrible hot spotting right on the chip. Then, between 2015 and 2019, the industry shifted to passive heat spreaders like pyrolytic graphite sheets and copper heat pipes. And today, from 2020 onward, we are fully in the era of phase-change materials and nanomaterial integration. The industry had to rapidly invent and adopt these advanced vapor chambers just to keep up with the extreme power of shrinking 3-nanometer and 4-nanometer nodes. All right, Section 3, inside modern cooling tech. Let's get under the hood and look at the current heroes of our thermodynamic mystery, vapor chambers and graphene. A vapor chamber works in a continuous, incredibly elegant 4-step cycle, relying on what physicists call the latent heat of vaporization. First, the working fluid, usually water or a specialized refrigerant, sits right at the hot processor and absorbs heat until it evaporates. Second, that vapor shoots away from the heat source at high velocity. Third, it hits the cooler outer regions of the chassis, condenses back into a liquid, and releases its heat. And finally, step 4, capillary return brings that liquid right back to start the whole cycle over again. It's like a tiny weather system inside your phone. But the real linchpin here is understanding step 4. Capillary action. This entire high-tech cycle relies completely on capillary action working its way through an internal wick structure. And this is absolutely vital, because if the heat gets so intense that the liquid evaporates faster than capillary action can return it to the heat source, the cooler completely dries out and just flat-out stops working. Then we have graphene. Now, in a pristine, ideal lab environment, a single layer of graphene has an astonishing thermal conductivity of over 5,000 watts per meter Kelvin. But in the real world, things like manufacturing defects, grain boundaries, and the simple fact that it has to be layered drastically lower its effective cooling power down to somewhere between 600 and 1500. So it's a great material for sure, but it's definitely not the magic bullet those lab numbers might suggest. Which perfectly tees up Section 4, the hidden physics bottlenecks. Because if the materials are so good, why is the heat still trapped? Let's meet the actual villains of the story. Just take a second and look at this number. Modern flagship chips generate an absolutely massive heat flux density exceeding 100 watts per square centimeter right at the active area of the silicon die. To put that into perspective, that is a staggering amount of thermal energy packed into a microscopic space. You can think of heat transfer kind of like a traffic jam. That graphene we talked about, that's your massive high-speed multi-lane highway. But the interface thermal resistance, the literal physical boundary right where the silicon chip meets the cooling hardware, acts like a single-lane toll booth. And it honestly doesn't matter how fast your highway is if the cars can't get past the toll booth in the first place. There's a temperature drop right at that interface that no amount of copper or graphene can just magically eliminate. The heat just can't get onto the highway fast enough. And to make matters worse, the bottlenecks compound. You've got the toll booth at the interface. You've got the vapor chamber hitting its dry-out limit. You've got chassis materials like glass that literally trap the heat. And ultimately, there's a strict volume limit. In a phone that's less than 9 millimeters thick, there is zero physical mass to safely store all that backing up heat.
So let's pivot to Section 5, how different brands adapt. It's fascinating to see how major global brands engineer entirely different philosophies to handle this exact same physical limitation.
As our sources show, Apple leans hard into a metal-first philosophy, utilizing stainless steel or titanium as a massive heat sink, tightly integrated with software that predictively throttles performance before temperatures even reach critical levels. On the flip side, Samsung and Xiaomi maximize passive hardware, aggressively expanding their vapor chambers to over 3,000 square millimeters just to absorb massive bursts of heat. And then there are the gaming brands. They basically throw their hands up at the surface area limits and just brute force it by adding active air convection using tiny internal fans.
But the brand is really only half the story. Your specific workload dictates exactly how the cooling system fails. Sustained gaming pushes the processor to a high thermal design power for a long, continuous stretch, which leads straight to that vapor chamber dryout we talked about. Conversely, running on-device AI models requires huge neural processing unit power that generates rapid, intense bursts of heat. And over time, those constant rapid thermal cycles actually cause microscopic structural fatigue in the thermal interface materials.
All right, looking ahead to our final part, Section 6, the future of cooling. Where on earth do we go from here?
To finally smash through that interface toll booth, future phones are going to need some radically advanced solutions. We're talking about micro-fluidic channels seamlessly integrated for active cooling. We're looking at AI-driven thermal scheduling that throttles very specific workloads based on the chassis temperature rather than just the chip temperature. We'll likely see advanced interface materials like liquid metal to drastically widen that bottleneck. Heck, there's even ongoing research into solid-state Peltier cooling pumps. As our source material perfectly summarizes it, vapor chambers and graphene are incredible, state-of-the-art tools, but they're really only one part of the thermodynamic equation. The overheating of modern phones is ultimately a fundamental conflict between the raw physics of heat dissipation and the industrial design mandate to keep our devices thin and sleek. Which leaves us with a final thought to ponder today. Until mobile silicon reaches some point of near-perfect efficiency where heat can be managed purely by natural convection, what happens next? Are we just doomed to experience thermal throttling as an inevitable quirk of pocket computing, or is every flagship phone soon going to need a tiny built-in fan humming away inside? It's a burning question for the industry, literally. Thanks for joining me on this explainer, and definitely keep an eye on how your own device handles the heat.